Good morning, everybody. Before we start, we must convey our deep respect towards the health workers of India, the doctors, nurses, the sanitized workers, also the policemen, towards their contribution of the health and wealth of the country. Okay, in this class, before we discuss, let me tell you that I will eat some abnormal things like, I will eat sulfur, hexafluoride, phosphorus pentachloride, I'll eat acetylene, I'll eat methane. Are you guessing now? No, actually, we will discuss the structure of molecule based on the hybridization. Okay? Before discussing hybridization in chemistry, we must discuss the hybridization in general sense. Okay? We are all familiar with hybridization in plants. As is shown in the figure, there are two brinjal plants. One having brinjal underdeveloped, in which the brinjal is not developed, not grown to the required size. Very small. We can't eat it. We cannot make business with that. Okay. Similarly, the another having developed brinjal but are affected, but are attacked by the insect, that are not also usable. We cannot make business with this. That's why we can hybridize both of the plants so that we will now get brinjal with improved quality. That means the brinjal of the hybrid plant will not be affected by the insect. Now we can apply this concept into the hybridization in chemistry. Okay? In chemistry, hybridization is a concept in which the central atom of a molecule or ion, before the bonds are formed by the central atom, the orbitals in the valence shell of that central atom intermix with each other to give some resultant orbitals, to give some orbitals, modified orbitals called the hybrid orbitals. These hybrid orbitals have the modified characteristics like shapes, energy, etc. And this should be noted that the number of hybrid orbitals is equal to the number of orbitals of the central atom those took part in the hybridization. And once the hybrid orbitals are formed, they must be arranged in such a manner that the repulsion among them should be minimum. And that's why they maintain maximum distance between them. That's give rise to a definite shape. The definite shape to the central atom, definite shape to the molecule. And then after, once hybridization takes place, once hybrid orbitals are formed, then after the bond is formed by the surrounding atoms. Okay? Based on the type of orbitals used in the hybridization, hybridization is classified into many types. SP hybridization, if one s and one p orbitals are taking part in the hybridization. SP3 D3 means if one s, 3 p orbitals and 3 d orbitals are taking part in the hybridization. Let us start one by one, and the first one is SP hybridization. Okay, we'll start with SP hybridization and we'll end with SP3D3. Okay, we will start with SP hybridization. You see here one s orbital and one p orbital intermix with each other to give two sp hybrid orbitals. Okay, so since only two sp hybrid orbitals are formed around the central atom, that's why two of the hybrid orbitals make an angle 180 degree, resulting in a shape that is linear. Okay, now for example we can take C2H2 ethyl, whose bonds are like this. Okay, if we'll take this carbon as the central atom, then this hydrogen and this carbon will be the surrounding atom. And if this carbon will be taken as the central atom, so there are two central carbon atoms, so the hybridization will take place in both of the central atom. Okay, so the electronic configuration of carbon is like this in the ground state, and the electronic configuration of that carbon in the excited state is one electron from the 2s subcell, 2s orbital is excited to 2pz, having each spp. Now all are having 1 and 1 and 1 electrons. So as we have already mentioned, 1s and 1p will intermix. Similarly, here 1s and 1p has been intermixed. This thing has been written for both of the carbon atoms. So you see this carbon will have two sp hybrid orbital, and this carbon also will have similarly two sp hybrid orbitals. How? But these two hybrid orbitals remain unhybridized, as I have shown here. These two will remain unhybridized. That may take part in pi bond formation. In case of C2H2, you see how this is the carbon, this is the carbon. These two are the sp hybrid orbitals making an angle 180 degree. These two are the hybrid orbitals of this carbon at an angle 180 degree. Here is the hydrogen making a sigma bond. When it overlaps head on the sp hybrid orbital, similar is the case here too. The remaining two p orbitals, this and this is the case of both the carbon. So these two of carbon and these two of this carbon are, you see how overlapping. This p and this p, this p and this p are overlapping sidewise to form the pi bond. As we see, these are the two pi bonds, one sigma bond. This sigma bond is the sp sigma bond. Okay, by the head on overlap here. So this is the sp hybridization. Okay. Now you see acetylene, the bond angle is 180 degree, making the two pi bonds by the sidewise overlap, and hence the structure of the molecule becomes linear. Okay, Similarly, in SP2 hybridization, 1s and 2p orbitals intermix to give 3 SP2 hybrid orbitals. Since 3 SP2 hybrid orbitals are present, they want to remain at maximum distance apart. That's why they make an angle 120 degree in space. Hence, that give rise to a shape trigonal planar. We can take the example of ethene. You see, we can take the example of ethene. The bond pattern of the ethene is like this. Similar is the ground state and similar is the excited state electronic configuration. But this time 1s and 2p orbital get intermixed and only one remain. Here also you see only one remain unhybridized that can take part in the pi bond formation. So, since there are more number of surrounding atoms, higher extent of hybridization takes place as compared to acetylene. So, the 3 sp2 hybrid orbital of this and 3 sp2 hybrid orbital of this overlap in a fashion like this. You see here, these are the 3 sp2 hybrid orbital of this carbon, means this carbon, and these are the 3 sp2 hybrid orbital of this carbon, means on this carbon. Okay, so hydrogen are making sigma bonds, means head-on overlap. You see head-on overlap or head-on overlap. Now we can say this is the sp2 hybrid orbital and this is the s orbital. They are overlapping head-on, hence sigma bond is formed, sp2 s sigma bond. This overlap is between two sp2 hybrid orbitals head-on, hence sp2 sigma bond. So, how the trigonal? You join this point to this point, this point to this point, and this point. So, this will give you a trigonal. Since in one plane, that is trigonal planar. Similarly, this carbon, you join these 3 hybrid orbitals like 1, 2, 3. So, here a trigonal planar is formed. These 2 carbon atoms also form trigonal planar. Okay. Here is the model for ethene. Okay. You see how it gives you trigonal planar. Bond angle here is 120 degree. Here also 120 degree. Making the structure trigonal planar. You join these 2 points. Now this 2 point and this 2 point. You are getting now a trigonal in one plane, hence trigonal planar. Okay. Now this is SP3 hybridization. That means 1s, 3 of the p orbitals will intermix with each other to give 4 sp3 hybrid orbitals. Since 4 hybrid orbitals around a central atom, that's why they tend to remain at maximum distance apart in the space, making an angle of 109 degree 20. It means each angle, this angle, this angle, this angle in the space. That's why that results in a shape of tetrahedra. For example, we can take methane. the bond pattern of methane are like this, all single bonds, no pi bonds are formed. And we have seen also this time all the p orbitals are getting intermixed, no p orbitals left to make the pi bonds. So here all of S and P are intermixing to give SP3 hybridization, and 4 SP3 hybrid orbitals are arranged in this way at an angle 109 degree 28 minute. Hydrogen with S orbitals are coming from the vortex of the regular tetrahedron. Here is the model for methane. You see, this is the angle 109 degree 28 minute, all these angles 109 degree 28 minute, making its tetrahedron. In SP3D hybridization, from the hybridization you see how many orbitals, 1s, 3p and 1d orbitals, means in total 5 orbitals are getting intermixed to give 5 SP3D hybrid orbitals. Since 5 SP3D hybrid orbitals, to maintain maximum distance, 3 of the hybrid orbitals remain in one plane, making trigonal, and the 2 remaining hybrid orbitals they are present in axial position, and this 3 in the equatorial position. The 3 hybrid orbitals in the equatorial position make an angle 120 degree and trigonal, and the rest 2 are present in the axial position. They make an angle 90 degree with the equatorial plane. As per example, we can take phosphorus pentachloride. Central atom is the phosphorus. The bond pattern are like this. These 2 are the axial chlorine. These 3 make the trigonal plane. Okay. So the central atom phosphorus, its ground state electronic configuration is like this. 1 electron from the S having 2 electrons is excited to the 3d orbital. Hence each orbital are now having 1 electrons. 5 orbitals like this get intermixed to give SP3D hybridization, and the bonding pattern of the hybrid orbital and the p orbital of chlorine is like this. As you know, chlorine make bond with its valence p orbital. We can see it by writing its electronic configuration. You see how the SP3D hybrid orbitals, these are the SP3D, 5 SP3D hybrid orbitals. These 2 are the 2 axial SP3D hybrid orbital. This is the chlorine bringing its p orbital and it overlaps with the SP3D hybrid orbitals head on to give SP3D, and this is p. We can take this bond is the SP3D, p head on overlap, hence sigma bond. All are like this, SP3D, p sigma bond. This is the p orbital of this chlorine, this chlorine, this chlorine. This is the case how phosphorus pentachloride is formed. Structure is trigonal bipyramidal. Okay. The model for phosphorus pentachloride. These are the chlorine. Okay. The third chlorine in the equatorial plane. Okay. When you join these 3 chlorine in the equatorial plane, that gives trigonal. Up is one pyramidal, down is another pyramidal triangle. In SP3D2 hybridization, in total 1, 3, 2 means in total 6 orbitals are getting intermixed to give 6 SP3D2 hybrid orbitals. All these hybrid orbitals are equivalent, making an angle of 90 degree. 4 of the SP3D2 hybrid orbitals remain in equatorial plane, and the remaining 2 SP3D2 hybrid orbitals make an angle of 90 degree or remain perpendicular to the equatorial plane containing these 4 SP3D2 hybrid orbitals. So, resulting a shape of octahedral. We will see this octahedral through model. You see, for example, we can take the sulfur hexafluoride. Central atom is the sulfur. The bond pattern of sulfur is like this. The electronic configuration of sulfur is in this way. Both 3s and 3px contain 2 and 2 electrons that can be excited to the vacant d orbitals. So, in total, these are 6 orbitals taking part in the hybridization like this. They are giving 6 sp3 hybrid orbital, and here you see how the bonding takes place in sulfur hexafluoride. You see here the 6 sp3 hybrid orbitals are there. These are the 4 hybrid orbitals remain in the equatorial plane, making an angle of 90 degree, to which these 2 sp3d2 hybrid orbitals make an angle of 90 degree, remain perpendicular. All f orbitals come with their p orbital, and this p orbital overlaps head on to give sp3d2 p sigma bond. All are like this, sp3d2 p sigma bond, all are like this. And due to lack of space, I have not made this p orbital. This is also a sp3d2 p sigma bond. This is the structure of SF6, the octahedral, and we'll see through the model. Okay, this is the model for sulfur hexafluoride. Bond angles shown are 90 degree. All angle in the equatorial plane are 90 degree. Also, the bond angle you see here 90 degree. Also, the axial fluorine atoms make an angle with the equatorial plane, that is also 90 degree. Here only the fluorine atoms have been shown at all the corner of a regular octahedron. You can imagine sulfur at the center of the octahedron, and then this is octahedral due to 8 triangular plane, hence octahedra. In SP3D3 hybridization, you see how 7 orbitals get intermixed to give 7 sp3d3 hybrid orbitals. Since 7 sp3 hybrid orbitals are there, they tend to remain at maximum distance apart. Hence, 5 of the sp3d3 hybrid orbital remain in the equatorial plane, making an angle 72 degree, to which the rest 2 sp3d3 hybrid orbitals make an angle of 90 degree and remain in the axial plane. Make an angle and remain as perpendicular to the equatorial plane. So these are 1, 2, 3, 4, 5
equatorial hybrid orbital. These two are the axial hybrid orbital. Thus, making a shape of pentagonal bipyramidal. 5 of the equatorial orbital make the pentagonal plane, to which the rest 2 hybrid orbitals make 2 pyramids, hence bipyramid. We will see through the model. As for example, we can take iodine heptafluoride. These are the bond pattern of iodine heptafluoride. The central atom iodine, having atomic number 53, has the ground state electronic configuration like this, in which 5d is vacant. These 3 fulfilled orbitals can be unpaired like this. The 3 electrons will be excited to the 5d orbitals. Hence, the 7 orbitals will intermix to give 7 hybrid orbitals, and the arrangement will be in this manner. Similarly, you see what happened in the iodine heptafluoride. In the equatorial plane, these 5 SP3D3 hybrid orbitals overlap head-on with the p orbitals of fluorine, making sp3d3 p sigma bond, and here the rest 2 sp3d3 hybrid orbitals overlap head-on with the p orbital of f. Due to lack of space, I have not shown you this p orbital of this fluorine atom. So this is the angle and this is the bond pattern. This is the structure of iodine heptafluoride. Let us make a model, and further we will explain. Okay. Model for iodine heptafluoride. These are the fluorine atoms. 1, 2, 3, 4, 5, 6, 7. Okay. Pentagonal bipyramidal. These 5 fluorine atoms make the pentagonal plane, and up and down 2 pyramid pentagonal bipyramidal. Okay. Thank you.